Welcome to G Fun Facts Online. Imagine looking at the weather forecast, but instead of a chance of showers, it calls for morning drizzles of liquid iron, followed by clear, scorching afternoons hot enough to vaporize metal. This isn't science fiction. It's the emerging reality of exoplanet meteorology, a field that is revolutionizing our understanding of worlds beyond our solar system. For thousands of years, we've wondered what other planets are like. Now we're finally getting answers, and they are more bizarre than we ever imagined. So how in the world do we study the weather on a planet hundreds of light years away, a planet we can't even directly see? Well, astronomers have become cosmic detectives, and their #1 tool is something called transit spectroscopy. This works when a planet's orbit takes it directly between its star and us here on Earth. As the planet transits, a tiny fraction of the starlight filters through the very edge of its atmosphere. Think of the star's light as a perfect, complete rainbow. As that light passes through the atmosphere, different gases act like tiny sponges, soaking up very specific colors of light. By capturing the starlight just before and during the transit, astronomers can see which colors are missing. This creates a unique barcode of absorption lines that reveals the chemical composition of the atmosphere. The James Webb Space Telescope has been an absolute game changer for this technique, allowing us to detect everything from water vapor to sulfur dioxide. While that tells us what's in the air, other methods tell us about temperature and wind. One technique is to watch as the planet disappears behind its star. Just before it vanishes, we see the combined light of the star and the glowing, heated day side of the planet. By digitally subtracting the star's light, we're left with just the faint thermal glow coming from the planet itself, which tells us the temperature of its hottest part. Taking this a step further, scientists can monitor a planet's light continuously through its entire orbit. Just like our moon, an exoplanet shows different phases as it travels around its star. By measuring these subtle changes in brightness, astronomers can create a rough heat map of the planet. These maps give us our first clues about winds, because on many of these worlds, the hottest spot isn't directly facing the star. It's been pushed sideways by winds carrying heat across the globe. But these observations are just snapshots. To truly understand the dynamic weather systems, scientists build these alien worlds inside a supercomputer. Using what are called general circulation models, or GCMs, they create a virtual laboratory. They input everything we know: the planet's size, its mass, its distance from its star, and let the fundamental laws of physics do the rest. The computer then simulates how energy flows through the atmosphere, driving winds, forming clouds, and creating global climate patterns over thousands of years. The biggest challenges are modeling things like clouds, which on these worlds aren't made of water, and photochemistry, which is how starlight itself can trigger chemical reactions in the air. When the predictions from these computer models match the real-world observations from telescopes, we know we're on the right track to deciphering the weather on another world. And the forecasts these techniques are producing are truly bizarre. Let's take a tour, starting with the most extreme examples: hot Jupiters. These are gas giants that orbit their stars in just a matter of days. This locks them into a fixed orientation, with one side permanently baked in eternal daylight and the other side in perpetual, frigid darkness. The dayside temperatures can exceed 2,000 degrees Celsius. That's hot enough to vaporize the very rocks and metals that make up planets. You literally get an atmosphere filled with silicate and iron vapor. Ferocious winds, sometimes reaching tens of thousands of kilometers per hour, then whip this rock vapor over to the cooler night side. And what happens when hot vapor cools? It condenses and forms clouds. On these worlds, you get clouds of liquid rock and metal. From these clouds, it's theorized to rain materials that are solid rock on Earth. On the exoplanet WASP Lin 76b, for instance, observations strongly suggest that the forecast calls for iron rain. The day side is so hot it vaporizes iron into a gas. Powerful winds carry it to the night side. where it condenses into droplets and falls as liquid iron rain. But it gets even more exotic. On the ultra-hot Jupiter WASP 121b, the conditions are just right for clouds of metals like aluminum and titanium to form on the night side. These elements can condense into corundum, which is the very same mineral that forms rubies and sapphires here on Earth. The forecast on WASP 121b could literally call for showers of liquid gemstones. A star's light doesn't just provide heat, it's a powerful chemical engine. High-energy photons can break molecules apart, and the fragments can recombine to form entirely new compounds. This process is called photochemistry. A landmark discovery by the James Webb Telescope gave us the first definitive proof of this happening on an exoplanet. While looking at a planet called WASP 39b, the telescope detected a clear signal of sulfur dioxide. This was a puzzle, because all the chemical models predicted that the planet's sulfur should be locked away in the form of hydrogen sulfide. The only explanation was photochemistry. The star's intense ultraviolet light was splitting water molecules apart. These created highly reactive fragments that then attacked the hydrogen sulfide, stripping away its hydrogen and freeing the sulfur atom to bond with oxygen, forming the sulfur dioxide that Webb was able to see. This was a watershed moment, confirming that fundamental chemical processes we see in our own solar system are also at play in these distant worlds. Of course, while worlds of iron rain are spectacular, the ultimate goal for many is to study the climates of smaller, rocky worlds, especially those in the habitable zone where liquid water could exist. This is where the story gets more complicated. A key question is whether a rocky planet can even hold on to its atmosphere. The case of GJ1132b is a cautionary tale. This world, slightly larger than Earth, was once thought to have an atmosphere. But more detailed observations showed it's most likely a barren, airless rock, its atmosphere completely blasted away by its nearby star over millions of years. This is a huge problem for planets orbiting red dwarf stars, the most common type of star in our galaxy. These stars are known for their violent space weather. They can unleash powerful stellar flares that bombard any nearby planets with radiation, stripping away atmospheres, destroying protective ozone layers, and likely making their surfaces totally inhospitable for life. Even when a rocky planet does have an atmosphere, it might be nothing like ours. We've discovered a whole new class of planets called steam worlds. These are planets larger than Earth but smaller than Neptune, and they have thick, water-rich atmospheres. They orbit so close to their stars that they are incredibly hot, and their water exists as a dense, high-pressure vapor, or perhaps even a strange state of matter called a supercritical fluid. We are truly living in a golden age of exoplanet science. The James Webb Space Telescope has opened a new window into these worlds, but it's just the beginning. The upcoming Ariel mission, launching in 2029, is designed to survey the atmospheres of around 1,000 exoplanets. This will move us from studying individual curiosities to understanding planetary climates on a grand, statistical scale. Ultimately, this all connects back to the search for life. An atmosphere doesn't just enable life, it can also hold the clues to its presence. By understanding what a lifeless planet's atmosphere is supposed to look like, with all its bizarre, non-biological chemistry, we can learn to spot the anomalies. The detection of certain gases that should NT exist together, like oxygen and methane, could be a powerful biosignature, a chemical fingerprint of life. So, forecasting the weather on alien worlds is about more than just satisfying our curiosity about iron rain and gemstone clouds. It's about placing our own planet, our own stable, life-giving climate, into a cosmic context. It teaches us just how fragile and special our world is, and it is the first critical step in finally answering that age-old question: are we alone?